Hello students, we are going to start chapter on column and struts. Columns are long slender members and they are designed to carry the axial load. Before we go on and develop the relationship for the buckling of the columns, let's first understand the concept of elastic stability. We know that when we have a short length bar and we subject it to compressive force, then the compressive stresses are induced in that. So suppose if the bar is subjected to a compressive force P, then the compressive stress will be induced of the magnitude P by A. But when the compression member is not short, the strut may not fail because of the compressive stresses, but it may fail because of the bending or buckling. So what we are trying to say, if there is a long slender member and if it is subject to axial stresses and we keep on increasing the amount of load, it may happen that it may buckle, and the failure may be because of the buckling or the bending of the column rather than because of the compressive stresses. So this critical load which causes instability or the buckling of the column and the failure of it, we need to determine that. Now let's first understand the equilibrium of an absolute rigid body. So there are three kind of equilibrium: stable, neutral and unstable. So that we can understand with the help of this perfectly rigid ball resting on different kind of surfaces. So in the first case, we have the ball which is resting on a concave surface. Okay, so we have a concave surface and the ball is resting on it, so it is in perfect equilibrium. If we push the ball either to the left or to the right side, it will raise a little bit on the surface, then again it will come down back to its equilibrium position. So every time it is moved from its equilibrium position, it has a tendency to come back to its original equilibrium position. Okay, so that's why this configuration is called as stable configuration. Now in the case when the ball is resting on a flat surface, and if we push it a little bit, it will move to another new position and it will not come back to the previous position of equilibrium. It will achieve another new equilibrium position, but it will not move further once we have removed the disturbing load. So that particular configuration is called as neutral. While in the case when it is resting on a convex surface, and if the ball is moved from the equilibrium position, the ball will have a tendency to always keep on moving away from it. Okay, so that particular kind of configuration is called as unstable configuration. Now let's understand this concept for the columns. So long columns have the similar kind of stability. So as you can see in the first example here, in the first figure, we have a column. This is the long column we are talking about. This is a long slender column, and it is subjected to a compressive load P, which is less than, let's say, some critical value of load PCR. So let's say we are applying certain 100 Newton, 1000 Newton load on this column. Now this column is in right now in equilibrium position, and if we apply a little bit of disturbing force on the lateral side, delta Q, this will cause this column to deflect in the direction of the force. So it will acquire this new position, and when we remove this delta Q or the disturbing load, this column will come back to its original stable configuration or the straight configuration. So this column is right now in a stable configuration, okay, because it is coming back to its original straight configuration after the removal of disturbing load. But when we increase the amount of axial load, the P that is we are applying, so let's say if we increase the value from P to PCR, which is certain critical value of the load, and if we apply again the disturbing force, it will achieve this new deflected shape. And when we remove this delta Q, even after that removal, it will remain in this deflected configuration. So the critical load is that value of the load, axial load, in which the column retains its new acquired equilibrium position, and it doesn't come back to its previous equilibrium position after the removal of the disturbing force. So that's why this is called as a neutral equilibrium or neutral condition of the column. Now, the third condition, when we keep on increasing the axial load, and if it becomes more than the critical value of the load, and if some lateral disturbing force is being applied, the column will keep on acquiring the new position. It will keep on deflecting. It has a tendency to move away from the straight configuration. So it will keep on deflecting and it will fail ultimately, right? So if the value of load, axial load, is less than or equal to the critical load, the column is not going to fail. But if it is greater than this value, the column is going to fail because of the buckling. So this is the concept of stability for the column. Now we are going to talk about a theory which covers these long columns. So this is called as Euler's theory, okay, and it is applicable to the long column that we are just going to see in a minute. And what is the meaning of long column? A column which is having length much higher in comparison to its cross section dimension. That means much bigger than its width and thickness. We are going to make certain assumptions. We are going to discuss those assumptions in detail, but for the beginning we can say that the material is homogeneous, perfectly elastic, and the column is perfectly straight, and the compressive load that is being applied is perfectly axially. Now at critical load, the column may buckle in any direction. So if you have a rectangular column, it may buckle either to the length side, either to the width side or to the thickness side. So if its moment of inertia is same about both the axes, it can buckle about any side. So that means if it is a square configuration, if it is a round column, so then it may buckle on any side. You can't really predict it. It can buckle on any side. But if it is, let's say, a rectangular column, then it is going to have moment of inertia on one side much higher than the other side. On one side it will be BD cube by 12, another side will be DB cube by 12. So because the flexural rigidity E times of I, modulus of elasticity multiplied by the moment of inertia of the body, depends upon the value of I. So the column will buckle about the axis of minimum I. So where the I is minimum, it is going to buckle on that direction. Okay. So if you see, if you take a scale and if you try to buckle it by applying a force on both the side, if you take a plastic scale, you apply the force, you will find that it will buckle on the width side, okay, never on the another thickness side. So because BD cube by 12, D is the thickness of that. So width is bigger, D is smaller. So BD cube by 12 is far less than the value of DB cube by 12. So that's why it will always buckle about on the lower side of flexural rigidity. So now let's talk about the assumptions that we are going to follow in the Euler's column theory. So first assumption is that initially the column is perfectly straight and the load is applied truly axial. Okay, so the initial configuration for all the columns are they are straight position and the load that we are applying is perfectly axial. The second is the cross section of the column is uniform throughout its length. So we are assuming a column which is not changing or varying its cross section. If it is rectangular, it is rectangular throughout its same width and depth, and or if it is square, it is square everywhere with the same dimension. The column material is perfectly elastic, it is homogeneous and isotropic, and thus obeys the Hooke's law. So we are going to assume that stress is proportional to strain, and the next is that the length of the column is very large as compared to its cross-section dimensions. So that's why we can consider it as a long column. The shortening of the column due to the direct compression being very small is neglected. So though we are applying an axial load, and because of the application of axial load, there will be axial strain that will be induced, compressive strain that will be induced, but that compressive strain is going to be very small, so we are going to neglect it for the purpose of our derivations. And the failure of the column occurs due to buckling alone. So there is no compressive stress involved in the failure of the column. So we are assuming that the reason for the failure is primarily due to the buckling only. Because we are going to deal with the bending moment and the equation of the deflection that we derived in our earlier class. So that's why we need to have some sign convention. Surprisingly, I am taking the opposite sign convention to what I took in the case of deflection of the beam, because the relation that I am going to use here, I have taken the same relation which is given in your book. So it is having EI d square y by dx square equal to m, bending moment, not equal to minus m. So that's why my sign convention will be opposite to what we proposed in the case of deflection of beam. So first sign convention is that a bending moment which tends to bend the column with convexity towards its initial center line, as shown in the figure 1, is taken as positive. So if you are having this kind of a convex shape towards its initial center line, then we are going to call it as a positive. Okay. And the second is obviously the opposite of that, that if the bending moment tends to bend the column with concavity towards its initial center line, as shown in this figure, it will be taken as negative. So we are going to say, okay, this is negative bending moment, this is going to be positive bending moment whenever the column takes these shapes. Now we will go one by one by taking different end conditions for the columns. So a column which is having its both ends hinged, okay. So you see the hinged end means pinned end, okay. It's like the hinges that you provide on your doors. So similar way. So you can't have the deflection, but you can have the kind of a rotation at that point. So there is a column which is hinged at both ends. So we have the column which is shown here at both point A and point B. It is hinged. You see this is a circle here I have made here at the end of the column. So this shows that it is hinged at these points. So column with its ends are free to rotate around the frictionless pin. Okay, it can rotate and take about these pins and which have been provided here. So the buccal shape is only possible when we reach the value of P equal to PCR. So this is the axial load that we are trying to apply on this column, and when this P reaches to the PCR value, some critical value of the load, this buckling is possible. Buckling will start. Before that, this column will remain straight, and there will be only compressive stresses that will be induced in it because of the application of load. So you have like you have a column which is hinged at both the ends. You start applying the load. You have 10 Newton force. Okay, it is still straight. You have 100 Newton. It is still straight. 500 Newton. It is still straight. 1000 Newton still straight. Let's say it reaches to 1500 Newton. And that particular movement, when it reaches to 1500 Newton, it may start to buckle. So that particular value of the load is the critical value of load, PCR, that we want to determine at what point this column is going to start buckle. So consider a section at a distance x from from the end A. So this is the end A. We are taking this point of the column, so which is at a distance x from the point A, and it is having a deflection y from the center line. Okay. Now, if you remember the deflection relation we derived in our last class, when we read the deflection of the beam, the relation was E times of I multiplied by d square y by dx square was equal to minus m there. But in the books, that the convention that we have followed, the books, it is written as positive m, so I am taking it as positive m because my sign convention is opposite to what I proposed in the case of deflection of beam, as I just told you. So EI d square y by dx square equal to m, bending moment. And because this particular shape I have considered as negative, you must have remembered that. I have just told you that this is a negative configuration here. We talked about here. So we are going to say that this bending moment is negative. So that's why this m is negative here. So what will be the value of the bending moment at this point? This will be load multiplied by the deflection. So load is being applied along this line, okay, and the distance of the load line from the point where we are considering the section is y. Okay, can you see that? This is my application of load line. This is my straight line on which the load is being applied, and this distance is y from the section where I am considering. So that's why the amount of bending moment will be load multiplied by deflection, that is P into y, and as I have considered it to be negative, so I just put in my minus sign over here, and I get this equation, which I can simplify and write it as d square y by dx square plus P divided by EI into y equal to 0. Now let's take alpha square is equal to P by EI so that we can get a simpler form to this equation. So for P by EI, I substitute here alpha square. Now this is simple second order ordinary differential equation whose solution is a harmonic solution, and we propose the solution as y equal to C1 cos alpha x plus C2 sin alpha x, where the C1 and C2 are the constants of integrations, which are to be determined by the boundary conditions or the end conditions of the column, right? Now let's determine the value of C1 and C2. Let's start with the point A. Okay, so at point A, that means at this point here, the x is equal to 0 and deflection is also 0. There is no deflection because it is a hinged end, so there is no deflection. Y equal to 0. If I substitute x equal to 0 in these here and put y equal to 0 here, so cos 0 will be 1, sin 0 will be 0. So this is going to give me C1 equal to 0. So first constant is C1 equal to 0. Now let's look at the other end. When x equal to L, because the length of the column is given as L, the deflection is still 0, y is equal to 0. So next time I am going to substitute for x, I am going to substitute here L and y as 0. It's because C1 is already 0, so that's why it will give me C2 times of sin alpha L equal to 0. Now either C2 is 0 or sin alpha L is 0. You see, C2 cannot be 0 because if C1 and C2 both are 0, then y becomes 0. If the C1 and C2 both are 0, then y becomes 0. And y is not 0 for all the position of x. So for non-trivial solution, it is necessary that sin alpha L should be equal to 0. So for if sin alpha L is equal to 0, then alpha L should be equal to n pi. Okay. And where n goes from 1 to 3, if you take the value of first eigenvalue, that is n equal to 1, so then alpha becomes equal to pi by L. Because we have just assumed the alpha as under root of p by ei, so you substitute it back there. So you write alpha square, so alpha square will be equal to p by ei, so pi square by L square should be equal to p by ei. This gives me the critical value of the load as pi square ei by L square. So this is the amount of load that is needed in order for the buckling to start in this kind of column where the both ends are hinged, where E is the modulus of elasticity of the material of the column, I is the moment of inertia of the column, okay, and L square is the length of the column. You see, this I will be different for rectangular on one different axis, okay. So the lower value of I we are going to put in here, okay. So BD cube by 12 will be there, not DB cube by 12 here. So the lower value of I will be here, so that the critical load will be having the least value, which will onset the deflection or the buckling of the column, okay. So this formula PCR equal to pi square EI by L square gives us the critical value of the load that will be needed in order for the buckling to start in the case of both ends hinged column. Now let's look at the second case. This is the case of where one end is fixed and the other end is free. So in this case, let end A be the direction fixed as well as the position fixed, and end B may be the free end. Okay. So you see here, this is like a cantilever which is straight and up, which is a upright cantilever. So one end is fixed and the other end B is free, and we are applying load axially here. That is the difference from the cantilever, because in the cantilever we apply the load in the transverse direction of the axis, okay. So here we are applying the load axially, and because of that, and we are having this deflected configuration which is shown here. So A is the deflection at the free end, so this is the deflection at the free end. At any distance x, the deflection is y. Again we will use the same formula here with which we have used earlier. So EI d square by dx square equal to m. What will be the value of the bending moment? Bending moment is always the load multiplied by the distance. So the load line is here. This is the load line, and this is the point I am considering for the section. So what is the distance here from the load line? So because this is A and this is Y, so this distance here will be A minus Y, okay, right? So this distance will be A minus Y. So you substitute here P into A minus Y. Remember here, this time I have given the positive notation here because my sign convention says this is a positive bending moment because of the way I have to consider my equation. So that is EI d square y by dx square equal to P times of A minus Y. Let me simplify this equation further, and let me write it like t square y by dx square plus P by UAI into Y equal to PA by EI. Now again we will take alpha square is equal to P by EI, and when we substitute for that here alpha square for p by ei both, this become again our second order ordinary differential equation, whose solution will be given by y equal to c1 cos alpha x plus c2 sin alpha x plus a. Okay, now with this general solution, we are going to start the task of determining the value of c1 and c2, the constant c1 and c2, and for that we will use the end conditions of this column. So at a, x is equal to 0 and deflection y equal to 0. You see, this is a built-in end, this is the fixed end. So at this end the deflection is 0, so that's why your y is 0 at x equal to 0. You substitute here x equal to 0 here, this will give you c1 cos 0 is c1 plus c2 is 0, c2 multiplied by 0 is 0, so c1 plus a equal to 0, so that gives me c1 equal to minus a. So first constant is determined. Now in order to determine the second constant, we need to apply the boundary condition on the we need to apply the boundary condition on the and a itself. So we have two boundary conditions for the case of cantilever end, that is deflection is 0 and the slope is 0, because it is a fixed end, so there cannot be any slope of the deflection here, slope of the column here, so that's why dy by dx should be 0. Now in order to find the dy by dx, let's first differentiate it. So if you differentiate this equation, you will get the dy by dx equal to minus c1 alpha sin alpha x plus c2 alpha cos alpha x. The differentiation of a will be 0, and when you substitute x equal to 0 here, so this term will become 0 and you will get c2 times of alpha equal to 0. This gives either alpha is 0, because alpha is not 0 because neither p, e or I is 0. So that's why that left me only option is c2 equal to 0. So we have determined both the constant. Let's put them back here in this equation. So you substitute c1 equal to minus a, c2 equal to 0 here, and then you get this equation as the form of y equal to a into 1 minus cos alpha x. Let's substitute back the value of alpha here from this. So you get a y equal to a into 1 minus cos under root of p by ei into x. Okay, so this is what we get here. Now you see at the free end, we know that at x equal to L, because L is the length of the column, the value of y is equal to a. So at this end, if you see, the deflection is y, so at x equal to L, the deflection y is equal to a. So you substitute this x equal to L and y equal to a here, and then you simplify it, the a and a will get cancelled out. This is going to give me cos of L under root of p by ei equal to 0. So cos something will be 0 only equal to when it is equal to pi by 2 value. So this gives me PCR value as pi square ei by 4L square. Okay, so we can calculate the value of critical load. You see, this critical load, if you observe here, earlier in the legs when the both ends were hinged, the critical load value was pi square ei by L square. Now this is 1/4 of the value that we calculated for the hinged end. So this column will not be able to sustain much load. It will fail much before our hinged end. So if one end is fixed, another end is free, such kind of a cantilever columns, if they are subjected to axial loads, you cannot apply much load over there. In fact, you can apply only 1/4 of the load that is being applied in the case of both the ends hinged. So let's bring this end to today's lecture, and we'll continue our discussion in the next lecture.